All right, so in this section, we are going to be looking at counting atoms and molecules by mass. So, if you've been to a grocery store or if you've bought things like salt, you realize that in a container of salt or kitchen salt or table salt, there are a lot of molecules in there. So instead of you going to a store and saying that you want 10 molecules of salt or you want 5 molecules of salt, you would rather say, okay, you're buying a container of salt that weighs 100 grams, okay, or that weighs 200 grams. So if you look at a container of salt, you will see that there is a net weight on it. So there is a mass. And so when we buy masses of chemicals, what we're actually doing is that we are indirectly counting using mass because a certain mass is usually equivalent or will usually contain a certain number of molecules. And that is what we're going to be looking at in this section, right? So chemists, they need a way to mathematically express a chemical equation. Okay, periodic table gives the formula mass of the elements. So if you look at this one, this image, you realize that I weigh 3 grams, right, of carbon. And so these 3 grams of carbon is equivalent to a certain number of carbon atoms. Okay. Or let's say I weigh 8 grams of oxygen. These 8 grams is equivalent or contains a very specific number of oxygen molecules. So it is much harder to count the number of molecules of oxygen because they are so small that the eye cannot even see. But but we can go ahead and do the counting, which is much faster by just weighing the number of oxygen or just weighing the number of carbon atoms. Okay. So what we use in this weighing is what we call the Avogadro's number. And so it relates the mass to the number of molecules. And so we're going to see that. So the Avogadro number is this magical number that we say 6.02 times 10 to the 23rd. Again, this is an exponential number with a lot of zeros. So if you look at them, you see this number here has about 21 zeros after the 2 if I had to write it out, right? And so because it is going to be very long, we use the scientific notation or the standard form to write the number out. Okay. So just look at the various elements right here. So this element here is sodium, right? This is a piece of sodium. And so this piece of sodium weighs 22.999 grams. And this 22.99 grams contains a certain number of sodium atoms, which is 6.02 times 10 to the 23rd. So if I weigh 22.99 grams of sodium, what I have indirectly done is that I have counted 6.02 times 10 to the 23rd atoms, right? The same thing for lead, right? If I weigh 207.2 grams of lead, it means I have indirectly counted 6.02 times 10 to the 23rd atoms of lead. And so this number is what we call the mole. Okay, so 6.02 times 10 to the 23rd atoms is equivalent to 1 mole of a substance. So the mole is actually a unit that we use for measurement in chemistry. Okay, hope that makes sense. So when we come and now want to translate this information into a chemical equation, like we saw at the beginning, what before this section we saw what chemical equations were. So when I write an equation like this with numbers, these numbers are called coefficients. When I write these coefficients in front of the symbols or in front of the formula of compounds, the way we read it is that 2 moles of hydrogen, because of these two right here, reacts or combines with 1 mole of oxygen to produce 2 moles of water, right? Now, what is the mass of these 2 moles of hydrogen, right? If you look at your periodic table, we saw that at the beginning that one hydrogen atom has an atomic mass of 1 gram. So if you look at how many hydrogens we have here, 2 here times 2, that gives 4. So since there are 4 hydrogen times 1, which is the mass of 1 hydrogen, that's why we say this hydrogen has a mass of 4 grams. Okay. And here, one oxygen atom is 16. And so, because there are 2 oxygen atoms, the mass of this oxygen atom right here, or this oxygen molecule, is going to be 32 grams. Okay. Same thing here. You add the mass of hydrogen to the mass of oxygen and you multiply that by 2. Okay. There are 2 hydrogen, 1 oxygen. So that is going to be 2, right? Plus 16. That's 18 times 2, which is 36. And and you got to know that the moles, depending on how many number of moles we have, we multiply that by the Avogadro's number. Okay, so if I have 2 moles, I multiply that by the Avogadro number. So 2 times 6.02 times 10 to the 23rd, that's what gives me this number right here. And so because I just have 1 mole here, it will be 6.02 times 10 to the 23rd times 1. That's why you still have the same number right here. But if you take these 2 and you multiply by this Avogadro's number, you will get this one. Okay. So the question here is how many moles are in 45.5 grams of chlorine gas? So the only way you need to look at it is that you need to ask yourself that how many what is the mass of a chlorine gas? What is the mass of chlorine gas? So if you look at the mass of chlorine gas, you realize that the mass of chlorine gas is 71 grams. Okay. So the mass of a chlorine gas is 71. So if this 45.5 grams is not up to 1 mole, it's not up to 1 mole. You need to convert this to moles. Okay. And so the way we convert that to moles is that we divide 45.5 grams divided by the mass of 1 mole of chlorine gas. 1 mole of chlorine gas has a mass of, let me find a pen right. 1 mole of chlorine gas has a mass of 71. Okay. So if you take 45.5, right, divided by 71 is going to give you the number of moles. Okay. And just take 45.5 divided by the mass of 1 chlorine molecule. 1 chlorine molecule has 2 chlorine atoms. So if you go on the periodic table, you will see that 1 chlorine atom has a mass of, I think it's about 35.45. So if you multiply that by 2, you will get something like 71 or approximately 71. So if you take 45.5 divided by 71, you should get that answer. Okay, just try it. Again, this is explanation here. Okay, so 1 mole of chlorine is 71 grams. So 45.5 grams is 45.5 divided by 71, and that's how you get that answer. Okay. So how many grams of water are produced from 1.25 moles of methane? So this is the explanation right here. So 1 mole of methane will produce 2 moles of water. Again, as you can read it from this equation right here, 1 mole of methane will produce 2 moles of water. Okay, so 1.25 moles of methane will produce what? You just multiply. So what you need to see here is that 1 mole of methane is going to produce the double. So the number of moles of methane is going to be doubled to produce the number of moles of water because 2 is a double of 1. So if you bring in 1.25, you just need to double that number, and that's how you get 2.5. Okay. So how many moles of carbon dioxide are produced from 50 grams of methane? Okay, how many moles of carbon dioxide are produced from 50 moles of methane? So with this one, you just need to do some conversion. Okay, so the first thing you need to do is 50 grams of methane, you need to convert that to moles. And how do you convert it to moles? You need to find the mass of 1 mole of methane. So if you find the mass of 1 mole of methane, you will realize that, okay, one carbon is 12 plus 4 hydrogen. Okay, so you have 12 plus 4, which is 16. So because there is a 1-to-1 ratio of methane to carbon dioxide, this is the same number of moles of carbon dioxide that will be formed. Okay, so if you convert this number of moles to grams, knowing that 1 mole of carbon dioxide is 44 grams. Okay, so if you take carbon dioxide is 50, okay, you divide that by the number of moles of methane. Okay, say how many moles of carbon dioxide are produced from 50 grams of methane. So what you do is you take 50 grams, okay, you divide that by 16, you will get 3.13 moles. That's how you get this answer right here. But that is going to be the number of moles of methane. But we know from this equation that the number of moles of methane will be the same as the number of moles of carbon dioxide. Why? Because they all have the same coefficients in front of them. Okay, there's a 1 in front of methane, there's a 1 in front of carbon dioxide, which means that whatever moles of methane is formed, that is going to, or whatever moles of methane we have, that is going to be the same number for carbon dioxide right here. All right, so I'm going to end this section, and we are going to continue in the next unit with reaction rates.